Okay, so our next talk will be by Kareem El Badry. Unless he has changed his title, this is what it says. The Galactic Underworld, the Milky Way's population of dormant black holes and neutron stars.
All right. Hello, everyone. Everyone hear me okay? Great to be back here. I think I'm the most recently departed ITC fellow. So I was here until a year ago, but already I can look back on it nostalgically. It was nice both to have so many cool people to talk to, but also what I didn't appreciate at the time, that I had basically the perfect combination of complete freedom and no responsibilities in a way that I probably won't have for a while again. I can wake up every day and basically decide, what am I going to think about today? So I'm going to start with a plot that Carl already showed a version of today. This is a census of all the compact remnants of massive stars for which we've measured masses, precisely measured masses. Up here we've got these merging black holes and gravitational waves. Remember, these we are seeing at cosmological distances all across the universe, but they're very bright in gravitational waves, so we can see them far away. Then we've got these X-ray binaries in the Milky Way, where a star is so close to a black hole that the black hole is slowly devouring it. And down here we have radio pulsars in binaries, mostly orbited by white dwarfs that they have previously stripped. And so these are all obviously very interesting objects, and we've learned a lot about them. But one of the things I want to emphasize is that these are all sort of unusual outcomes for massive star evolution. And they're also not, especially for the neutron stars and the X-ray binaries, we don't get to see pristine black holes and neutron stars. We see them after they've accreted, in some cases, a lot of material from a companion. I'll start with a few open questions in this field that we hope to address. First of all, what are the masses, spins, and birth kicks of black holes and neutron stars? We have some sense that, we have the masses here, they're on the y-axis, and we have some spins, although we might not believe them. But these are not the typical outcomes. And so what we'd like to know is what is the whole population, if we could see everything. How do these quantities depend on properties of the progenitor star? Things like on the mass of the star, on its composition, on what kind of environment it formed in. How do black hole and neutron star binaries form, evolve, and survive? Most massive star binaries, even if they start out in binaries, don't make it to this stage. Either they merge earlier or they become unbound. And finally, what else lurks in the dark? And the point I'll make here is that the techniques I talk about, we can basically detect anything compact that exerts a gravitational force. So we expect to find black holes and neutron stars. We'll also find lots of white dwarfs, but we could also find more, maybe we could find a black hole that was less massive than a neutron star, or certainly we can find binaries with two compact objects. So we can cast a wide net. So we've got this iceberg. And nowadays, the tip that we can see that's relatively easy to find are these X-ray binaries and gravitational wave sources. But these are both rare outcomes of binary evolution. And so just for reference, within the Milky Way, if you want to detect a gravitational wave merger, you have to wait about 10 to the 7 years. And about 1 in 10 to the 4 massive stars that forms a black hole will end up in a gravitational wave merger eventually. Fun fact, these low-mass X-ray binaries are even more rare. Only about 1 in 10 to the 5 massive stars ends up in one of those. But we do see 20 or so of those in the Milky Way, but probably 1,000 or so in the Milky Way, because they live much longer. We can observe them for of order of billion years. But then underneath, we've got this bigger population of isolated black holes that aren't orbiting anything. We can only see their gravitational effects by lensing. Or black holes in just wider binaries where you do have a star orbiting them, but not so close that you see accretion. And just in the last few years has it become feasible to find both of these populations. So far still in small numbers, but we hope soon in large numbers. So all of this is everything I'm going to talk about is enabled by Gaia. We've heard a little bit about Gaia, but I'll play this movie. So Gaia is basically a spinning top in space. It's got these two cameras that sweep out an arc on the sky, and then the axis of rotation precesses, and so over time can cover the whole sky. And the period of this precession is 63 days. So on average, every 2 months or so, Gaia returns to each part of the sky and takes another measurement of where the star is at that point. Right? That's all Gaia does, is measure where are the stars. The amazing thing is it measures this really precisely with an astrometric precision of down to 0.01 milliarc seconds for bright stars. So what is 0.1 milliarc seconds? So one way you can think about this is if I'm in California and I look over at Massachusetts with my telescope, 0.1 milliarc seconds is the width of a human hair. This analogy often impresses the public, but astronomers are kind of used to ridiculous scales. So another scale that is maybe more impressive, this image here that the EHT took, this is 10 times larger, the scale of this image, than the precision with which we can measure astrometry with Gaia. Obviously, Gaia could not make this image, but this is made by a global interferometer and a 747 full of hard drives, whereas Gaia is a 1 meter telescope in space making these measurements for 1 billion stars. So it's really amazing. So Gaia does this over time, and eventually, after 3 years or 5 years have passed, you can put together all these measurements and fit orbits to them. You find many stars are not in the same place every time, even after you correct for parallax and proper motion, but they're going around in circles like this. And we can use this to measure the masses of the companions. So people have been thinking about this for about a decade now, of finding black holes with Gaia. As usual, it all started with Avi. So Avi had a paper in 2017 with Natalie Machian, where predicted how many black holes could you find with Gaia. And in the abstract, they said 2 times 10 to the 5. And you can see over time, people have kind of gotten more pessimistic. That 2 times 10 to the 5 was basically saying, if every massive star becomes a black hole, and and assume they all have companions at the separation range where Gaia could detect them, how many would they detect? But they did a smart thing, that classic theorist trick, where in the actual paper they said, well, the number is 2 times 10 to the 5 times some uncertain factor f, which could be 1 or much less than 1. So really, they're probably right no matter how many we detect. The reason these numbers went down, I think partly the field got a little less optimistic, but the main difference is accounting for things like dust in the Milky Way, and then really accounting for binary evolution. That the kind of separations Gaia is sensitive to, many of the companions that are initially there around massive stars might not survive when the stars become black holes. And we might start with some optimism, because already before Gaia, there were lots of discoveries of non-accreting black holes in the last decade or so. But you shouldn't be so optimistic starting out, because it turned out a lot of these objects weren't actually black holes. And so I was at the ITC for 2 years, and so the first year was this period, and this was my proudest accomplishment during that period. And then in the second year or so, the numbers started going up again, but fortunately it never got negative. And so the population we can actually study has now been increasing. So I'll just talk briefly about what we can actually measure with Gaia. We have some star, mass M star, going in an ellipse, semi-major axis A star, around a dark companion. So Gaia measures the parameters of this ellipse, measures the period, the shape, how far away it is from the parallax. And then we can also estimate a mass of the star. If we get a spectrum, we know how bright it is, and it's a normal star. And we can just plug these parameters into Kepler's third law, and we can almost just solve for M2. The only challenge is that the A that goes into Kepler's third law is really A star plus A2. We don't know A2. But we can do a little algebra. We rewrite this in terms of a mass ratio. And we get an equation like this that basically only has one unknown. It has a bunch of parameters. If we know M star, then Q and M2 are the same unknown. So we can solve for what M2 should be given these observables. And then we can say, what can go wrong? Well, the basic thing that can go wrong is the companion could be a luminous star instead of a dark object. And in that case, what Gaia sees will be the photocenter, so the light-weighted mean position of the two stars. And that will trace out a smaller ellipse than the star itself, which is also smaller than the full semi-major axis. And so if we use this equation to calculate M2, we'll get a number that's much less than the true M2. And that's really why astrometry is good for finding black holes and why it has very few false positives. It's that if you have a luminous companion and you don't realize it's luminous, you'll estimate a lower mass than if you had assumed it was dark. Sorry, if you assume it's dark and it's actually luminous, you'll underestimate the mass. And so you get very few false positives. Here's sort of a simulation illustrating this point. So don't worry about the relative numbers of objects in the population, but here I assume I have some luminous binaries, I have some triples where I have a luminous star and a tight binary, then I have some stars orbiting neutron stars, some orbiting dark companions, and this is just Kepler's third law, right? As you get more massive, you go in this direction. And so astrometry is very good for finding black holes because these populations separate out nicely. There will never be two luminous stars in a binary that end up in this part of the population because they both have lower masses, but more importantly, they have light blending that makes the ellipse that we can measure smaller. Okay, so in 2022, while I was here, we had the third data release of Gaia, which was the first one that had binary orbits. And we got this period distribution of astrometric binaries. And what I've compared it to here is the best period distribution of astrometric binaries we had before, which is from Hipparcos. Hipparcos measured 235 binary orbits, and Gaia gave us 200,000. And so Hipparcos wasn't the only binary survey before, but even if you consider all spectroscopic surveys or astrometric surveys where you get an orbit from which you can compute a mass, Gaia was about a factor of 50 in sample size. So if you want to find a rare object, it's a good place to look. The reason there are no objects with a period of 300 days is a year is a difficult period for astrometry. So we immediately want to start following these up spectroscopically to characterize the stars, confirm the orbits, but you can't follow up all 200,000. So we tried to select the sources where we find that the mass of the dark companion is more than the mass of the luminous star and is more than the Chandrasekhar mass. So if everything goes well, it should be a black hole or a neutron star. That gave us something like 50 targets. So these are mostly bright stars, but they're relatively long periods because with astrometry, the longer the period, the bigger your ellipse, the easier it is to detect. And that means you have to be a little bit patient to do this follow-up. So how does this follow-up work? Well, I was lucky to be at the CFA where we have a lot of time on the trace spectrograph. This is a 1.5 meter telescope at Mount Hopkins run by Dave Latham. And then in the south, we use a 2 meter telescope. And we've had just a ridiculous amount of time on these two telescopes. These are basically sort of semi-retired planet hunting spectrographs in that they're quite precise, but not precise enough to find the most exciting planets anymore, but plenty precise to follow up signals from black holes. And so the way this works, that we have an astrometric orbit. It predicts what the radial velocity should be doing as a function of time. So then we go measure a few radial velocities. And sometimes it looks like this, where the astrometric orbit predicts a huge signal, but in fact, you don't see any variation. And so the point is Gaia is very good, but when you look at a billion stars, anything can go wrong, and sometimes things go wrong. So this is why spectroscopic follow-up is important. In other cases, you have something like this, where Gaia makes a prediction, but the ephemeris is uncertain enough, because it's based on data a few years earlier, that there's a good amount of scatter in the prediction. And then you measure a few radial velocities, and it looks like they're moving in the right direction. But if you then jointly fit the astrometry and the radial velocities, then you can get a tightly constrained orbit, even though you only got 3 RVs, which wouldn't be enough if you didn't have the astrometry as well. So the first exciting discovery we had was this black hole. Carl already talked about it a little bit. This is a half-a-year period, sun-like star in the disk, orbiting around a 9 solar mass black hole, moderately eccentric, and only 500 parsecs away. So at the time, this was the closest black hole by about a factor of 3. Just a few months after that, we had another one, again about a 1 solar mass star, about a 9 solar mass black hole. Longer period now, more than 3-year period. So if it were much longer, Gaia wouldn't have been able to get an orbit at all. About a kiloparsec away, so this was at the time the second closest black hole. This star is on the lower giant branch, so it's a little bit more luminous. You can see it farther away, but qualitatively pretty similar to the first one. And then we thought we were, we did our astrometric selection early, and we thought we were done as far as black holes. So we started working on neutron stars, which I'll get to in a moment. But then just a month ago or so, there was this exciting discovery of a third one. This is based on astrometry that's not published yet, but will be public for all sources in DR4. And there's an even longer period now, almost 12 years, and a mass that's much higher than anything we had before. One of the nice things about these kind of objects compared to gravitational wave sources is we can get spectra. We can get really nice spectra of the stars. So we can measure metallicities, and we can also measure abundances of like 20 other elements. So you can see here's Gaia BH1, its spectrum. There's a metal-rich solar metallicity star. Gaia BH2, the really massive one, very low metallicity. And so in the future, we'll measure probably millions of black hole masses in gravitational waves, but you'll never get a spectrum like this, right? You'll never know what was the star that produced it. And here, for each one we get, it doesn't actually matter how it formed, whether it formed from a isolated binary or from a cluster. Either way, we expect the companion will have the same composition as the progenitor of the black hole. Of course, the first thing right here where everyone's excited and says, well, this is the first empirical proof that low metallicity stars make massive black holes. But then you say, well, wait, what if it's 2 black holes? Right, all we know is the total mass. So it could be 16 plus 16, or 16 plus 17, rather than 33 solar masses. We can actually test that. So we haven't done it yet for BH3 because it was just published a year ago, but for the first one, BH1, my student Pranav Nagarajan led this. And this started shortly after we published BH1. I talked to Dave Charbonneau, who's good at measuring precise radial velocities, looking for planets. And these kind of bright stars are exactly this kind of stars. They're slowly rotating solar-like stars that people look for planets around. And so the idea is if you have a star orbiting 2 black holes, when you zoom out, the orbit looks exactly like a star orbiting 1 black hole with twice the mass. But when you fit a Keplerian orbit, you get these residuals, right? You have one residual on half the period of the inner binary. It's like this rotating dipole potential. And then you also have a longer time scale thing because the inner binary makes the outer orbit precise. And so if you get precise radial velocities, you can make this measurement. And so we did this for BH1 using Espresso at the VLT and KPF at Keck. For both of these, we can measure radial velocities at something like 3 meters per second, which is pretty competitive. And so first of all, this is the discovery data for this object. You can see here our uncertainties were on the order of kilometers per second. And then we got some more data. What's shown here is the data with uncertainties of a few tens of meters per second. So if you zoom in, you say, well, it still looks probably consistent with noise. Maybe there's some signal in there. But then here's another level of precision. We can zoom in again. And it turns out as far as you zoom in, the noise always continues to look consistent with noise. So we don't have we can always get a good fit with a Keplerian orbit. And based on that, we can actually rule out basically all plausible double black hole or any kind of inner binary companions. And so that's illustrated here, the dashed lines are how good of a fit we get with a 2-body orbit. And then these colored lines are what is the expected goodness of fit if we had an inner black hole with different eccentricities and mass ratios and things like that. And the punchline is we can rule out inner periods of more than 1.5 days. If the inner period is too short, then it just looks like one black hole and you can't tell. But if the inner period is less than 1.5 days, then it will merge in a Hubble time. And so you'd have to have been very unlucky very fine-tuned to observe it just as it was about to merge. So for BH1, we know it's not two black holes. And for BH2, we can do the same thing. We just have to wait 12 years for us to gather these radial velocities. But this is a simulation that Pranav did. And you can see if we get the same quality data, we can rule out interperiods more than 5 days. But because these black holes are more massive, 5 days is the shortest period within which they wouldn't merge in a Hubble time. So then we have 3 black holes that look qualitatively like this. The question is how to form them. And as Carl talked about, it's not easy. So the first thing you might think is, put a massive star there. Say a 40 solar mass star will give you a 10 solar mass black hole at solar metallicity. If you do that, the star expands, it becomes a red supergiant, and it gets much bigger than the current orbit. This is a problem for all stars that we've discovered orbiting black holes. So the normal answer is you have a common envelope, and if you're optimistic, the liberated gravitational potential energy as you plunge in can eject the whole envelope, and you can end up in a post-common envelope binary with a helium star and another star, and that can collapse to become a black hole. But the challenge is you only get enough gravitational potential energy to eject the envelope, we think, if you spiral in all the way. So the challenge with these is that it's like they spiraled in a little bit and then stopped. And so Carl talked about dynamical formation channels. These seem pretty interesting. So there have been a few papers about these ones and then also about BH3. I will say I don't think it's totally settled yet. The part that makes me uncomfortable is that for most of the simulations of dynamical formation, you don't actually avoid having a common envelope. So you see in both this paper and this one, you still have a common envelope that you somehow escape with a wide orbit. The main difference is that you've had some stellar mergers before the common envelope, so you have a little bit different stellar structure. And it's certainly plausible that this happens. I'm sure it produces some of them, but we still have some work to do in checking these stellar evolution calculations and predicting what the post-common envelope properties should be. For BH3 in particular, I think the dynamical formation is really promising because it's in a stellar stream. Single metallicity stream, probably formed by a low metallicity cluster. And so it seems like it's very naturally produced by these kind of models that Carl talked about. So here's our population. This is orbital period. This now is distance. So over here you've got all the X-ray binaries and then a few radial velocity binaries. And you see all of the new binaries from Gaia are much wider periods. It's not surprising because they're not detected in X-rays. These are only detected in X-rays because they're close periods. But they're all closer than any of the previously known black holes. And we think we're not at a special place in the universe, so close is just a proxy for common. And probably there are just a lot more of these than there are these. There's also this one just a little bit farther away black hole so far detected by microlensing where we have an astrometric measurement of the mass. And we hope to find lots more in both of these populations. Even though these are wide and we don't expect there to be a lot of accretion, never hurts to look. And so shortly after I had this discovery, I got an email from Ito and Yvette Sendes that said, why don't we look at this in radio? So we did. And then got another email from someone at Chandra that said, why don't we look at this with Chandra? So we did. This was eventually analyzed and written up by grad student Tony Rodriguez at Caltech. So no detection, not so surprising because we think accretion is very inefficient in these kind of systems. But one interesting takeaway from this modeling is that we do eventually expect to see accretion when the companion stars become red giants. And that phase when they're red giants and they're dropping winds or Roche overflow is pretty short, only a few million years compared to a lifetime of a few billion years. But those kind of systems you can probably see all across the Milky Way. And so based on the number that we see with Gaia, we predict that there should already be some giant plus black hole symbiotic X-ray binaries. And the eROSITA survey, which has had its first data release, we hope will detect them. In addition to black holes, we find a lot of white dwarfs in the same kind of orbits. So this is work done by my student Natsuko Yamaguchi. What's plotted here are about 30 of them where she's done spectroscopic follow-up. But if you just look at the astrometric one, we have like 5,000 white dwarf plus main sequence star at 1 AU separations. So they're much wider than sort of traditional post-common envelope binaries down here. And we infer that the rate of these two populations is actually about the same. We just didn't have any of these wide ones before Gaia because the shorter period ones are much easier to find with radial velocities and with light curves. And so Natsuko has been working on a population model, modeling both the Gaia ones and self-lensing binaries from Kepler, which we had a few of before. And the takeaway is about 1 in 100 solar-type stars has a white dwarf companion at these separations, and we hadn't found hardly any. Okay, the last ingredient is neutron stars. So we have about 21 of these, done lots of radial velocities. Remember, each data point here is an observer staying up for a night. Here's a little movie that I'll play as we're finishing, showing their orbits. And the red, each time there's a red scan, that's a Gaia measurement of where the luminous star was at the time. And so we don't really know these are neutron stars, right? We know that their masses are above the Chandrasekhar mass and that they're dark. So neutron stars are our best guess. Could be two white dwarfs in a close binary, but that's hard to do from an evolutionary perspective. Skip that. Last thing I'll say, we can look at the mass distribution of neutron stars and black holes. And we see this gap between neutron stars and black holes. You know, it's partly small number statistics because we don't have a lot of black holes. But remember, it's easier to detect a 3 solar mass black hole than a 1.5 solar mass neutron star. And we detected 21 of these and nothing in between. So we can certainly say very confidently that in these kind of orbits, there are more neutron stars than low mass black holes. Can't yet say whether there are more low mass black holes than high mass black holes. We can't rule out that there are a few low mass black holes, basically. But if you look at all the black holes and neutron stars for which you have masses now, as a function of orbital period, we've got all these Gaia neutron stars, pulsar neutron stars, X-ray black holes, Gaia black holes, and we've got a nice line between them. So far, we found 2. But we're optimistic that in DR4 we'll find a lot more. And so just taking the rate we get from DR3 and predicting forward, I'd guess of order 100 in DR4. The last thing I'll say is we're organizing a KITP workshop to talk about these kind of objects, also gravitational wave populations and X-ray black holes, gravitational or black holes at the nexus, about 1.5 years in the future. So mark your calendars. And my summary is it's not yet raining these kind of black holes, but it's at least a drizzle, and we're optimistic for more. Thanks.
Thank you, Kareem. Avi.
So what is your expectation for, of course, there is the population that is very difficult to detect except for microlensing, which is the rogue black holes. And how, I mean, there is a very large uncertainty. There is one detection so far.
Yep.
And what's your expectation?
Yeah, so I think Roman will find at least a dozen or so of those. They are, I mean, my guess is in 10 years we'll have more from these kind of binaries than we do from those. The challenge is the way we follow them up now, we only follow up long duration events, and we have to do it one object at a time with HST, which is expensive and means you'll only be biased to low velocity black holes, basically, because they have high velocities, they won't have a long duration, you won't select them in the first place. With Roman, that won't be the case because you can get astrometry for everything. But the forecasts are not quite as high as these. So it depends on what cadence Roman chooses. I'm confident we'll get some, but my guess is it'll be in the ballpark of 10.
Yeah, fantastic stuff. Question about the system where you repeatedly zoom in with with RVs, and you get a really nice Keplerian curve.
Right.
What are the limits on additional mass that is external? So you basically are able to say that it's not two black holes.
That's right.
What about other mass?
You mean within the orbit or farther out?
Farther out.
Farther out, yeah. So there's some limit. So there's a plot in our paper. I think it's inner periods of or outer periods of less than 100 years roughly we could rule out things down to the hydrogen burning limit. As you get farther away, eventually you would be resolved. So we don't see a spatially resolved companion. But I think periods like 200 years or something like that are still consistent with that, and that might actually help make this kind of system by 3-body. So it's a good argument to keep getting these kind of RVs.
Thank you so much. It was a wonderful talk. I have a question about the neutron stars, maybe mainly because you didn't get a lot to talk about them. So I had a question. It was hard for me to understand what are the periods that you get, and from the periods that you get for the neutron stars, can you constrain the kick recipes or kicks of neutron stars that you will get, and formation scenarios in general?
Right. Yeah, so here they are. So the periods are basically 200 days to 1,000 days, set almost entirely by the Gaia observing strategy. So it's almost the same period distribution as normal binaries observed by Gaia. You'll only end up, it depends how they formed, but by isolated binary evolution, you'll only end up in these kind of periods if you have a weak kick. Otherwise, you get unbound. Something like 50 to 100 kilometers a second is the limit. And then you basically have the same problem you had for the black holes. You have to survive the Kalman envelope and not get too tight. So I would say it's an unsolved problem how to form them in the first place. It's also harder to appeal to dynamics for these because neutron stars the black holes are more massive than anything around, so they're more likely to switch out with companions. But neutron stars are about the same mass as other stars in their birth environments, so dynamics seem to be less efficient at forming these in clusters. So problem to work on how to form these neutron star systems.
Last question.
Hey, yeah, great talk, Kareem. So Gaia BH3 should be bound to become brighter, hopefully, in about 10 years. Have you tried to estimate what's the peak accretion rate in terms of Eddington that you can expect?
Yeah, we did do that. I forget the number, but we just compared it to BH2 because BH2 has a giant that's about the same size. And at periastron, BH3 is about, I think it's about 4 or 5 AU separation, which is about the same as the BH2 average separation. But it's a more massive black hole, and it's twice as close. But it's a low metallicity giant, so its winds are weaker, and we don't know exactly how much weaker. So our ballpark is that it should be about the same kind of limit as BH2, or the same expected X-ray flux at periastron.
You have any announcements? Let's thank Kareem once again.